Hello everyone. So as Professor Pratik Pal said that Professor Anjanananda Sen was going to take the class, as you all know, and he was the best person who could have taken this class. But I'm sure you will get another chance to learn from him. I'm going to, I mean, anyway, since he has developed different models of dark energy, this with Professor Sherar, and afterwards he has done phenomenal works on dark energy, and some of them I'm going to share with you in the next class, where he works with the consistent equation of the scalar field model of dark energy, quintessence model, and tomorrow we are going to discuss that along with several other parameterization. So as you can understand that it is his model, so he's the best person, but we'll try to do, nevertheless, try to learn as much as possible. Okay, uh, I have already shared the Google Doc with you. Uh, some people have joined late, so if you are not able to see the chat box, let me just share it with you again. Uh, let me share my screen. All right. So, uh, unlike the last four classes where I had spent one class for the theoretical development, and the next class was on hands-on session, depending on the theoretical development. These two classes will be a little bit different. I'm not going to discuss too much theoretical aspects on dark energy. I mean, there have been many developments on dark energy. For example, not just quintessence model, not just the background evolution, dark energy perturbations are there that affects the CMB CMB temperature and polarization anisotropy spectra at intermediate and small scales. Those are very important topic, and one of the solution of H naught problem, if you remember, I discussed that the CMB constraints on H naught, the Hubble parameter today is nearly 67.4 plus minus 0.5 or something like that. And on the other side, the local Hubble measurement from HST, from Rees et al., is, or different other observations are pointing towards a very high value of H naught. Of the order of 74 plus minus 1.5. I forgot the exact number, but it is nearly 2% or 1.5% measurement. So there is a very strong tension between the early universe observation like CMB and the late universe observation. Um, Dark energy, specifically early dark energy, can solve this problem. There has been several papers written, but these, although they can solve the problem, there are lots of fine-tuning issues, etc. I would urge you after this lecture, have a look at those papers as well. For example, phantom dark energy as well, what we are going to discuss tomorrow again, are able to solve this type of problems. So dark energy is not just important to solve the supernova that we are going to supernova distance modulus that we are going to learn now. It is also important to solve cosmological tensions. Okay. Yeah, that is what I wanted to mention before I start on dark energy. And first of all, let's discuss what are the parameterization. Okay. So let's say if we have for photons, baryons, we know that their properties, right? We know their scattering amplitude, we know their mutual, for example, we know that electron scattering, electron proton scattering, electron photon scattering. So we know these particles. Okay, we know these particles, so we do not have to parameterize those particles. What we need to parameterize is that the total energy content of those particles, those matters or those radiations. Even in most of the cases, they also don't need to be parameters. For example, as you have noticed, when I calculated the energy density of the of the radiation today from the temperature, you understand that this temperature, you can think that this temperature TCMB can be a free parameter, but we have been able to detect TCMB to an unprecedented accuracy. So it is 2.7255 Kelvin. So omega radiation is not a free parameter anymore. We know it precisely, 2.4 into 10 power 2.47 10 power minus 5 H in H to the minus 2, right? And in the units of sorry, in the omega in the units of critical density. So we have taken the ratio. So we do not need to parameterize this. Also understand that when we talk about radiation, we know its equation of state. So we know what how pressure and energy density are related. The equation of state is 1 by 3, W equal to 1 by 3. If I say rho equal to P by 3, yeah, P equal to rho by 3, then W equal to 1/3. And we know that matter acts as a dust, pressureless dust, so its macroscopic pressure is 0. So we do not have to parameterize that as well. So the only unknown parameter here is the total matter density, and total dark energy density is simply coming from the matter density, because it is 1 minus omega matter, because the total density as we have assumed is as we have normalized is 1. Now here comes the another part of the puzzle. If there is curvature of the curvature, then spatial curvature of the universe, then we can parameterize it with omega k. We remember I have defined omega k as minus capital K divided by a square h square, where k equal to +1 0 -1, depending on the open closed and sorry, open flat and closed universe. The omega lambda is uniquely determined if we know omega m in a flat universe, or if we know omega m and omega k in a non-flat universe. So therefore, dark energy in this case also, when we are assuming dark energy to be driven by the cosmological constant, we know its inner equation of state, that is the equation of state of dark energy is cosmological constant is W equal to -1. Okay, so if it is -1, we know that omega lambda is completely constant over time. Sorry, the energy density of the dark energy remains constant over time. It doesn't change, and therefore it is a 0 parameter. So this lambda CDM model is a 0 parameter description of dark energy. Okay, so today what we are going to discuss is we are going to constrain this 0 parameter model of this dark energy. Now, okay, as I was saying that these two lectures will be a little bit different. So in both these two lectures, we are going to have a big part as the hands-on session. Okay, and also we are going to discuss the data analysis methodology, how to do Markov chain, Monte Carlo, etc. Now the dark energy is mainly different, as you can understand from it. The properties of dark energy is mainly different from the matter and the other known components of the universe, or even unknown. For example, dark matter, other components of the universe can be, I mean, you can differentiate between them by saying that how much expansion it can provide. We discussed in that plot that if radiation is there, then we have decelerating expansion. If it is matter dominated epoch, then it is also a decelerated expansion, but it is a lesser, it has a lesser deceleration parameter. So Q for matter dominated epoch is less than Q for radiation dominated epoch. And then we have dark energy dominated epoch, where we do not have deceleration, but we have acceleration. So dark energy is a form of energy that provides an acceleration in the universe. Okay, And in order to understand that, constrain that, the best probe is the supernova. Okay. Here whatever we discuss, this distance measurements, etc., are going to be useful. You remember we discussed there are several distance measurements. One is co-moving distance, radial distance, which increases and then stays nearly constant. We discussed angular diameter distance that increases and then reaches a peak and then decreases. So those distances are not going to be useful to understand supernova. So let's talk about what a supernova. Supernova is explosion of stars in binary systems. Okay. Whenever this kind of explosion happens, one particularly interesting property of this supernova explosion is that they have a peak brightness which is uniform. So we always say that these are like 100-watt bulbs. Okay, so there are, like, you can think that you are in a playground, and there are lots of 100-watt bulbs that are there around you at different distances. And so you can say, you can put 100-watt bulb at 1 meter distance, another one at 2 meter distance, and then you can put it up to 100-meter distance. And since they have a uniform brightness, they can be used as standard candles. So even if you do not understand you do not have a measuring tape, let's say, in order to measure the distance between the farthest bulb to you, that is the 100-meter, let's say, we assume that, but the person who is doing this experiment doesn't know that. Even in that case, if the person is supplied with this information that these are standard candles, so they have uniform brightness, then the person can do a calculation saying that, okay, this is my brightness. So the apparent brightness that I am receiving from each of these bulbs are decreasing over distances. Therefore, I can simply take this L by 4 pi r square measurement and say that what is the R where the luminosity is L, let's say the 100th bulb. Okay, so simply I can see that, and it is the inverse square. It decreases with the inverse square law in order to preserve that energy, because as far the energy goes, as I discussed in my first lecture, that the radiation had to cover a higher surface area, and the surface area grows proportional to r square. All right. So therefore, we can simply say that which bulb is at what distance, although we cannot directly measure the distances. This exact same problem is there in the universe. So we cannot go to another galaxy and measure its distance. Yes. Please.
Sir, I have a doubt. How can we be sure that all the supernova had the uniform
from brightness? The theoretical, okay, so this is something that is one can get the supernova light curve spectroscopy and understand. This is also from the theoretical modeling people have been able to understand, and also you can simply, there are other measurements. Okay, it is not just the supernova is a good measurer of the, or measuring scale of the universe at different at higher redshift, but so there are supernova explosions that are recorded in the vicinity, in our vicinity as well. So when we have detected them, we have found them to be having the same absolute brightness, similar distances having the same not absolute brightness, yeah, you can say absolute brightness, having the same brightness, who are supposed to be at the same distances. How we know the distances? For example, we can also know the distances from the galaxy's luminosity, etc., the radiation, and for example, there can be other absorption profile, right? So let's say there is some we have the spectroscopy of a star, and from the spectroscopy we know these hydrogen helium lines, right, the absorption lines, and from those lines we know that this line has to be at a particular rate, at a particular wavelength, but they don't match, the wavelengths don't match exactly because of the redshift. So we can, from the redshift, we can see that what is the wavelength shift, and we can understand that this is the wavelength of a shifted wavelength of that star, and from that we can understand what redshift that star is. Okay, so now understand that we detected two stars, or let's say two very nearby galaxies, which are of same distance, similar distance, and and we see supernova in them. Okay, and from there we can say that these two supernova have the same distances and have the same brightness. So therefore we can understand, this is just a very vague description that I have given. I mean, uh, people do much better analysis. It is not as simple as that, but this is one of the way. Okay, how you can measure the how you can understand that the two supernova having the same absolute brightness. Does this answer your question?
Yes, sir. Thank you.
Okay. Now, as I said, their apparent brightness gives away the information about the expansion of the universe. So you understand that, okay, these two, so you understand this luminosities don't match together. So the distance that I was thinking that the supernova is situated, that is not the actual distance. So that means that we are seeing an expanded distance. Okay, so we can, from there we can understand that the universe has expanded, and from there we can even understand how they have expanded. So one of the main quantity that we are going to detect, we basically detect from this supernova is this distance modulus, which is the difference between the apparent and absolute magnitude, which we define it like this. And this distance modulus is written as 5 log dl in parsec minus 5. If I change it to megaparsec, it becomes m minus capital M is 5 log dl in megaparsec plus 25. So we use the luminosity distance and feed the supernova data. Okay, and the data can be downloaded from here. You can just go click on this link and go to that link and then download that. So it has it lists 580 supernova. So this is the union of supernova. So there are lots of supernova surveys that detected different supernova, and they detect at different redshifts, and some detect at for a range of redshift. So what union does is that union basically takes the light curve of the supernova, analyze them in a same umbrella, in the same umbrella of let's say I mean same analysis umbrella, and then you get the distance modulus of all of them, and you download the error coverage matrix. And what we are going to do is that we are going to download the data and plot them with errors. Okay, and for example, these are the just the absolute magnitude. For example, this table shows the measurement of the absolute magnitude of the nearby supernova, and these are the name of the supernova. And okay, so for example, here you can see that how the amplitude, okay, you cannot see how the amplitude is calculated, but there are different software, there are different techniques in order in understanding the supernova absolute magnitude. So the paper that you can have a look is this paper, the ABJ paper, and you can see these are the absolute magnitude, which you can see is varying from 19 to 19.5. So as I said, this should have the same absolute magnitude. That is also not true. So they have a fluctuation. Okay, so the fluctuation is there, but still they are very good in order to be treated as standard candles. All right. So what we need to understand is that we have to marginalize over this absolute magnitude or things. And again, so if we know the absolute magnitude of supernova, understand that this part, this DL contains this integration. Okay, integration dt over at, remember, and this has 1 over h naught. When you expand that integral, 1 over h naught times the integral, in the denominator you have square root of omega matter times a power minus 3 omega lambda plus omega lambda plus omega radiation times a power minus 4, etc. So there h naught is there, that is coming out of the denominator, coming out of the factor. And if you know absolute magnitude, you can detect h naught. But the thing is that we do not know absolute. We basically know that absolute magnitude have a range. Okay, absolute magnitude is not constant. So h naught, it is very important to understand that h naught is actually degenerate with the absolute magnitude. So therefore, it is very important to appreciate that point, that we cannot constrain H naught with the high redshift supernova. Okay, so you can do that, but these are with the low redshift supernova. But with the high redshift supernova, which we talk about talk for constraining the dark energy, these cannot constrain H naught. We are going to see that when you marginalize over the magnitude, when you use the covariance matrix with the real data, with the systematics included, then you will see that we are not able to constrain this H naught. Okay, so these are different supernova.
Excuse me, sir.
Yeah.
Sir, can you please repeat that? Why cannot constrain the H naught for the high
I'm going
redshift
to,
supernova?
yeah, I'm going to show it to you by hand. Okay.
Okay.
So, yeah.
Okay,
So
sir.
we are going there. So you'll also be able to do that. So these are the supernova with the error bars. So error bars are this basically diagonal terms of the error covariance matrix. And the supernova, the main papers where these supernova nova were reported are given here. So these are the complete set of 580 supernova given by the Union 2.1 compilation. Okay, so this is a compilation, as I said. So what they did is that they have added all of them. Okay, and put them in the same analysis umbrella. Yeah, and this is the distance modulus. So this m minus capital M mu. So and the best fit theoretical curve, as you can see, is simply this. We are going to calculate that. We are going to see it in the notebook that you just plot this data, and once you plot that, then let's talk about the least square fit or the goodness of fit. Okay, we already discussed that in the CMB lecture, but I basically rushed into the last part of the lecture. I mean, I got it very fast, so therefore I would like to speak here slowly so that you can understand what is going on. So if we have, let's say, n data points, say n equal to 580, let's say we have 580 supernova, which has the data given as di, where I runs from 1 to n, errors as sigma I, and we estimate our theory ti for a given set of parameters that we collectively call as theta. Okay, then the goodness of it is given as chi-square if the errors are not correlated with each other. So if there are the first point, and so if the data are not correlated, first data point and the second data point are not correlated, then the diagonal term of the covariance matrix becomes 0, right? Therefore, you do not need to worry about that. This is the least square fit, or basically, sorry, this determines the chi-square. Okay, and when you get the best fit, that is called the least square fit, where the chi-square is the least one. Okay, where the chi-square becomes the lowest. For example, here you can see that this is the best fit theoretical curve, the black line, right? But if the data points are correlated, then the off diagonal components will cease to be 0. They will have different values. Okay, apart from 0. So given the error covariance, the chi-square can be written as this. Okay, so it is di minus ti transpose. So you write a data vector. You take the residual data vector in the residual space. So it is the di minus ti. That is the one column vector. Let's say you transpose it, that becomes a row vector. And this one is the inverse covariance matrix. So you can simply understand that it is the inverse covariance matrix because the diagonal term of the covariance matrix is the sigma square. So if the covariance matrix doesn't have any off diagonal terms, then if you take the inverse, so these are basically the 1 over the diagonal terms, right? The inverse of a matrix is 1 over its diagonal terms if the matrix is diagonal. Now, simply this boils down to this value. So this chi-square definition boils down to this definition if the diagonal terms are 0. As you can appreciate, it becomes 1 over sigma I square. All right. So then simply this becomes dot product, and it's basically the square in the denominator. And now we talk about the likelihood. From the least square, the likelihood can be obtained as minus 2 log likelihood equal to chi-square. Okay, so likelihood is basically exponential of minus chi-square by 2. And for smaller number of parameters, one can simply do a grid search. Let's say I have 2 parameters. What I can do is that I can say that I break my parameter space into 10 cross 10 grid, and I search in between 10 cross 10 grid. So it is 100 data point that I have to 100 parameter values that I need to search. So it is not a problem. We can do a grid search. We are going to do the grid search, okay, in the notebook, and we'll see that it is not very efficient if we want to get accurate answer, or if the number of parameters increases. So you can simply understand this is a grid search in the 2-dimensional, then it will be a cubic grid search in the 3-dimensional space. Then it will be higher dimensional if it goes on and on. So highest likelihood or the least chi-square represents the best fit, and the probability density decreases as we go away from the best fit. Okay, and yeah, for Gaussian posteriors, for example. So what we are talking about is the Gaussian posterior. And once you get the posterior, you simply, let's say you have one parameter. Then in one parameter, you will see that the likelihood, this is the likelihood I am plotting for one parameter. You will see that there is one point where it peaks. That is the maxima, where what did I say? The highest likelihood, okay, or the least chi-square, exponential minus chi-square by 2. So this is the least chi-square point. So at this point, my distribution of the parameter becomes maximum. And if we go for different other parameters, I see that my fit decreases. Okay, so the chi-square increases. So at some point of time, we'll see that the area under the curve between this point and this point will be represented by 68%. Okay, you see in this side it is 34%, and this side it is 34%. This value is called 1 sigma. Okay, so this is the standard deviation. For a Gaussian, you know what is the standard deviation. So if you represent this, if a posterior of a parameter, if the posterior of a parameter is Gaussian, then simply you can say that say the 68% is enclosed by so yeah, in both sides, this 34%, 34%, you can are symmetrically distributed if it is Gaussian, and then you can say that these are plus minus 1 sigma confidence contour. In those cases, just twice of that sigma is called 2 sigma, which actually corresponds to 95% confidence level. Okay, and then it becomes higher, then it becomes basically 99.7 or something like that, and those are called 3 sigma or something like that. Okay, and just a second. Yeah, so you see 2.154% and 2.14%. So these are nearly 4.2%. So it is 1 minus, if you subtract them, then you can find that this is 95%. 2 sigma is 95% confidence, and then it is 98%, I think. Okay, the rest part. So yeah, so what we need to do is that we need to get the confidence interval for the cosmological parameters. Okay, using these confidence intervals if they are Gaussian, or otherwise you can simply say that if they're not Gaussian, then there are different techniques. Generalized techniques. Just you should have to understand what is the posterior mass. For example, if you are doing a Monte Carlo, in that case, you can understand what is the region where most of the 68% mass of the points, or the consideration of the points are settled in. So you can identify that as the region of 1 sigma there. Okay. Similarly for 2 sigma and 3 sigma. 2 sigma is 95%, etc. Okay, and in this example of constraint, often you didn't type 1 is supernova data. Omega matter is the relevant parameter if we assume the universe is flat. H naught is degenerate with the absolute magnitude. This is what I wanted to mention. We are going to see that. Therefore, H naught constraint from the supernova union data does not represent the actual constraint. And also, if you have 1, 2, 3 parameters, degrees of freedom. So these parameters are called degrees of freedom. So you are varying these parameters freely. Okay, and you are trying to understand what is the best fit, or what are the confidence region of that parameter. So these parameters are called free parameters, and that is why we call it call this number of parameters as the degrees of freedom of that theory. And there are simple calculations that shows that if it is degrees of freedom is 1, then then if you do this chi-square analysis, and if the delta chi-square, where in the region where the delta chi-square drops as 1, then that region is called 68%. Then drops as 2.71 is called 90%, and it is not 2 sigma. Okay, this is 2 sigma, but this is not 2 sigma. And if it is 99%, then the delta chi-square will drop by 6.63 if the number of degrees of freedom of your theory is 1. If it is 2, then you will see that more number of degrees of freedom will bring in more flexibility always, right? So then if you calculate this analysis again, so it will be bivariate Gaussian distribution, right? So this is a simple Gaussian distribution. And if you just go for higher and higher parameter, if they are Gaussian, then it will be it will be described by multivariate Gaussian distribution. So this is 2, and then this is 3, and then it becomes multivariate. So there, the 1 sigma region is described by a delta chi-square of 2.3 delta chi-square is called 68%, and for 3 parameters, delta chi-square of 3.5 is representing the 68% significance. These are all for Gaussian calculation. Okay. Now let's fit to the data. If there are no matter, okay, if omega matter equal to 0, that means your omega lambda equal to 1. So we are just trying to see by eye whether we are able to fit the data. So these are the data points. And if you are able to see that most of the data points actually are going below this line or these points are actually my theoretical line or theoretical values of the DL at these redshifts. Your omega lambda. So there are no free parameters. Omega lambda equal to 1. And I have plotted this DL. So this is not a good fit to the data, as you can simply understand. If I have 0 dark energy, so that means that your omega matter equal to 1 or omega matter equal to omega total equal to 1 and your omega lambda equal to 0. There are no dark energy. So you can simply say that most of the data points are above this. Okay. So this is not a good fit to the data either. Even without doing a chi-square calculation, you can say that. Qualitatively, you can say that. Okay, we are going from one stage to another. We are trying to see what we can do, what we can say about the data or about the theory given the data, even without doing any calculation. Okay, calculation of chi-square. Of course, you have to do this DL calculation and compare, right? So, so each of these data points, or each of these parameter values, let's say omega matter equal to 1 here or omega lambda equal to 1 here, are basically samples in the omega matter parameter space, single one dimensional parameter space. And you can see that these are not fitting well. Now, if you take the best fit, if I, for example, have 30% matter and 70% of dark energy, you can see that these are going from the middle, right? So by eye, you can say that these are going through the middle. So this is, so as you can say that, okay, roughly my theory is constrained to have 30% of matter and 70% of the dark energy. All right. We are going to calculate that. And this is where I have written that constraints on H0 does not reflect actual constraint as it is degenerate with absolute magnitude. So DL, if you remember this DL calculation, we are going to show that it has 1 by H0, dt by H0 square root of, so you can change dt to dz as well. So integral dz by H0 square root of omega matter times a power minus 3 omega lambda plus omega radiation times a power minus 4. So this H0, and the left hand side you have m minus capital M. So this is the this has the absolute magnitude. So if I let's say my absolute magnitude is minus 19, but I say that, okay, if the absolute magnitude is minus 19.5, because I know that there are variations, okay, then what is going to happen? So we do not know the absolute magnitude. So H0 is simply proportional to the absolute magnitude here in the theory. Okay, so if I assume them to have the same magnitude and we know that absolute magnitude, then we can, to a very good precision, then we can constrain H0, but it is not really the case. So it becomes completely degenerate. So this is something that I am going to show, that we are going to get a constraint if we do a toy model analysis, but this is not a correct answer. Okay, so this is something that you have to keep in mind when you do the analysis, and we are going to derive the correct answer later. Here, what I have done is that I have done this analysis, but I have removed the diagonal terms of the covariance matrix. So what I did is that I have used the simple chi-square formula here, data minus theory by sigma whole square sum over all the data points. And okay, so these will be the assignments that you can do at home. I'm going to go for the Markov chain Monte Carlo, but I'm going to show the notebook first before going there. These are the assignments. So obtain the best fit for a non-flat universe. You have to change the equations. Okay, change the equations means that you have to take into account this sine or sine hyperbolic terms. Plot the 2D map of minus log likelihood. Importantly, plot the L by L max for the flat case. Plot the contours and find the standard deviation, and remove the data before and after 0.75. Remember, so this is 0.75. Let's say, okay, midpoint. Let's say up to, it goes up to 1.4 redshift. So you take the data before and after 0.75 and obtain the constraints from both and plot the likelihood. So now let us go to the lab. This is another one. Data constraints. Yeah. This file is available here. As you can see, Dhiraj notebooks. Okay, so I would urge you to download this file, TIH3DE1.IPyNB. Okay, this is available here. Or if you want to have a quick, just a second, let me open the chat box. If you want to have a quick check in your computer, local computer, then I can provide that as well. You have, okay, so I have provided that in the chat box. You can download that, but remember, you have to keep it in the same folder where this constants.py and plankbf.py files are kept. Okay, you remember that we had discussed this in the same context, in similar context, where we have used this constant values like the velocity of light, etc., capital G, and the Planck BF are the Planck best fits, where Planck best fits where we have used them if we don't want to do an MCMC or something like that. Just use the Planck best fit and plot the quantities. Okay. So remember, these are the Friedman equation again, H square, equation of H square and H dot, and you define redshift as given, you define the scale factor with for a given redshift as 1 by 1 plus z, and you define d eta, d of conformal time, and you also define eta. Okay, these are all for the cases where we are talking about flat universe. Okay, moving distance, you have to change this according to this integral. So f can be plus sine or sine hyperbolic, or just simply x, f of x can be x, so if it is flat. So these are the definition. Remember, we discussed angular diameter distance, luminosity distance, distance modulus. Okay, just give me a feedback whether you are able to run this. Please write in the chat box if you are able to run this in your own machine. Running in Psi server. Okay, that is good. Even if it is running in Psi server, it is fine. Your own machine should also work. So I assume there are no problems. Yes.
It is showing that failed to process string with text because letters could not be found.
Okay, LaTeX is something that you have to just uninstall or
Okay.
simply. Okay, there was one student who said that this package has to be installed, pip install. I forgot the command. Oh,
Sir, I did that pip install LaTeX, but
it is not LaTeX. I think it is something else. I think
okay,
Python LaTeX or something like that. I don't recall exactly.
okay. I will remove all the commands for LaTeX then
Yeah.
to run.
Okay. Let me check. Yeah, it's pip install LaTeX. Is it installing or not?
Sir, I have installed it, but even after that, it's not working.
Install
I have
PyLaTeX
installed.
with PyLaTeX,
Okay, sir.
or just simply search with your error command. It is going to show what you need to install. Okay.
Yes, sir. It was saying that I have to
Have you
install
installed
some
Matplotlib?
like yes, sir.
Okay. Anirban
Uh,
Chandra is saying got the distance modulus curve. Okay. So see, distance modulus curve is nothing but the luminosity distance in just a specific format. 5 log 10 distance modulus plus 25. Yeah, luminosity distance. And if you go to this co-moving, yeah, just look at this line. Okay, if see what I'm highlighting. Okay, Bhaswati is saying module not found on traceback. Import constants as constants. Oh, okay. This is something. Oh, no. Your constants.py should be there in your folder. It is known as theory constant. Then just say theory constants. Yeah, change to that. You say import theory constants as constant, const. That is because in the Psi server there was a problem. I noticed. I changed it to theory constant because it was showing that for Psi p there was some other module named constants. So if you change that, then it should work. In my machine it is constants, and it doesn't give any error. So yeah, if you see that here, notice a square h is h naught, right? And I'm taking d eta. Everything what we are doing, this is the main integral or the main integrand. Sorry, it is not an integral, it is integrand d eta. We are simply integrating that d eta from 0 to some a in order to get the values, in order to get the distances. So in the denominator you have 1 over h naught. Okay, you got the distance modulus, and then you plot the union 2.1 data. Okay, good. Got the plot by commenting the LaTeX commands. That is fine. I think you can simply just plot title. If you there, I'm just using this LaTeX command. You can simply just get rid of that, and this dollar signs. You can just get rid of that for the timing. These are just cosmetic changes, so not. I mean, your physics is not going to change if you change that. Okay, age of the universe, something that I have kept it here because we sometimes use that if we want to plot this instead of z, but only for
sir,
reporting
excuse me,
purpose.
sir. Can you please provide that union.txt? It's saying that by SN union text not found
Yes, yes,
in the
yes,
code.
yes. Sorry, let me just compress data. Okay, it is being shared with you in that chat box, but I am also sharing that. Oh, by the way, I had written that copy that Cosmo MC folder. Have you copied the Cosmo MC March 2014 folder? But don't copy it in your the Psi server. Psi server is not working with the MPI F90. If any of you, I think some of you will have MPI F90 installed in your machine if it is Linux machine. In Windows machine also probably you can do that. I haven't done that, but probably you will be able to do that. If it is Unix, then you will be able to get the MPI F90. Anybody having this MPI F90 in your machine? Module not found error, import lang bf as pl. Um, oh, okay. In the Planck BF, just say theory. Okay, yeah. Theory constants as CNST. I have written as CNST, but no module named theory constants. But if you have theory constants here, then it should show module theory constants, right? I mean, if you go to the left-hand side where all the files are kept, you should be able to see the theory constants, no?
Sir, according to what you said, I changed the name theory constants as constants, and after that I tried compiling
Uh,
the Python notebook,
no,
but
no,
it
no.
is showing.
You keep the
Yeah.
theory constant as theory constants because constants is some module in the SciP. So what you do is that here in the program, in the code, import constants as const, just say import theory constants as const, but keep the name of this file as theory constants. Okay.
Okay, sir. I'll try.
Yes.
Thank you.
Yes, Anubhav, you can install using MPICH. I think there should be some. Yeah, MPI-CH is one. There are several MPI provider. CH is one of them. You can use OpenMPI. Yeah, just use OpenMPI version. Yeah, sudo apt-get install OpenMPI bin. Okay, I think there should be a devel version as well because these are there are some development packages that you might need that that will be needed. So if you cannot do that, do it after this class, and I'm going to show how I'm doing this parameter estimation with Cosmo MC, and I'll explain everything. So I will urge you to go back to the notes and again do these things, okay, with the MPI F90. If some of you do not have your MPI F90 access, then you ask your institute. Your institute must have some Linux machine available. Data file in the Sci server. Yes. I'm sorry. Hmm. Okay, in the notebooks, I'm keeping them. Okay. Okay, I have uploaded this data.zip file in that notebook folder, so you can simply use that. Okay. And what you do is that you just keep it in the same folder, please, because it is going to, because I mean, as you can see, I am just reading from the data folder. I mean, that is inside that folder um, where your notebook is kept. Okay, so here I am plotting this with the diagonal, with the error bars only. Okay, and then what I'm asking it to plot is that for zero. Okay, so this is, I think, wrong, because it is saying zero dark energy, but it is fitting them. But the only thing is that what you need to do is that you need to change somewhere. I think I have made it. Yeah, omega lambda 0 L is 0. Okay, not here. I'm sorry. I was compiling here. Okay, so this is, I'm Okay, I think I have to put it as 0L. Yeah, this is where I had overwritten there, but yeah. So you see, I am using omega lambda 0 lambda as 0. I hope you are able to follow this, right? Omega matter is 1 minus omega RB, because if omega lambda is 0, then omega matter for a flat universe is just 1 minus this radiation density. Can you just say yes if you are able to understand?
Yes, sir.
Yeah. Then please just run this cell by putting omega matter 0 lambda and omega lambda 0 L. So using these keys, and I hope that you are able to see these ones, right? So this is what I had. It is still not reading. Have you unzipped the data? Unzip data.zip. Unzip the data. I think you can. Can you unzip here directly? No, right? No, you have to. You have to do it in the terminal. Yes, terminal. Because yeah, I mean, I could not upload a folder there, so that is why I had to upload it in a file format. Okay. So you have to do that. Unzip that and see that, and this is what I showed you, right, in that plot. Now let us just see. Okay, there. Okay. OS error trackpad, plot figure.
Sir,
Yes.
sir, in Python notebook, that file is not uploading. After that, I think we have to upload the text file from the data. Complete folder cannot be uploaded, and the RAR file is not uploaded.
I haven't.
It cannot
uploaded,
read that.
No, I have uploaded the zip. That is why I have uploaded the zip. You have to go
Zip
to the
file.
terminal.
Yes.
Yeah, terminal, and unzip it.
Okay.
Also, have you done that? Because I'm seeing it is not able to load the data, right?
So where is the data zip folder, data.zip folder?
It should be there in that in Dhiraj notebooks, data.zip here. In the same notebook, if you go to the terminal, see, I'm going to the terminal. I'm showing you the steps. Okay, so let me CD.
So have you just uploaded it?
I was uploading it since I think I uploaded it 5 or 7 minutes ago.
Okay, just let me check.
Okay, so you can also, okay, let me just unzip here itself. Unzip data.zip. So as you can see that now the folder is also there. So you can also SCP from my folder to your folder. If you want to know the path, this is the path. I'm also putting it in the. Anubhav is saying I am getting the module SciP optimize has no attribute CKM. Oh yes, that is the problem. It is you have to, if you have to say theory constants as CONST. So you cannot say constants as CONST. Theory constants as CONST. Okay, let me show you. Okay. HEORY. Yeah, this one.
Hello, sir.
Yes.
Just Zoom was just went off for me. So I have copied that data.zip folder in that notebook folder itself. So
File, not folder.
that is a
Yeah,
data.zip.
it is a zipped file. It is a so I have zipped that folder into a file. So you have to unzip that.
So what is the command for unzipping it?
I did it. You can also simply copy it from here. As I said, you can. So this is the name of the notebook folder. You can simply copy the whole notebook folder into your directory again if you want, or you can also simply copy this capital DATA folder inside the notebook to your folder. Anyone will work.
Oh, Okay. Data folder, right?
Yes, data folder inside the notebooks folder, and keep it in the same folder where your notebooks are.
Okay, let me do that.
Yeah. And
So,
Anubhav,
sir,
So sir, should we
import
unzip the data
constant
folder?
as constant. That is not working. Import constant as constant.
yes, that is not working because this in the version of SciP that is there inside that inside the Sci server, that has a optimize which has a constant high s dot constants module, which is conflicting with the name that I had given. So what I did is that I have changed the name of the, if you are able to follow my highlighting in that screen, I have said import theory constants as CONST. Does it work or it is not working? Now it worked. Anubhav is saying is work. So you do two things. Just one thing, I think, because I had already changed this constants to theory constants in the name of the folder. See, this folder is named as theory constants.py, right? And here, sorry, not this one. Okay, I have already opened this here. So here you just say import theory constants as CONST. That's it. Okay. So Anubhav says it worked, and two of you were speaking. I just answered to one of you. So the second student whom I could not answer, please say what you are saying.
Sir, should we unzip the data zip file?
You can do that, or also I have unzipped it for you. See, it is the data. The data is already there. All the data are there. JLA.
Okay, sir. Now I have to copy again from your folder. Okay.
Yeah, if you have the unzip thing, then you don't have to copy from my folder. You say unzip, then just give the file name. It should work. Unzip data.zip. It should work. You don't have to copy again.
Where, sir? Where in the terminal?
Yeah. Here I did it, right? You see unzip.data. You are able to see what I'm highlighting, right? Here.
Yes, sir. Yeah. Wait, sir. Wait. Just wait.
Unzip data.zip. See? As soon as you do that, you will be able to see this data folder.
Sir, this fitting that we have done just now, it is for the zero matter content, right?
Fitting means visual fit, right?
Yeah, this one.
Yes, visual fit. Yes, omega zero. So no, this is zero matter content is now I am doing. The last one we had done was for zero lambda. You see, omega matter was 1 minus omega radiation, omega r background, sorry, omega r baseline, and omega lambda was 0. So now I am giving it.
So what is this? Omega m0m is the omega matter content which you have set now to 0.
Yes, now here it is 0. You see, I've defined two sets of variables.
Okay.
Let me just plot this one. As you can see, what I was showing, you will get this kind of plot. Okay, so I hope that others will be able to catch up soon. So I'm going to the goodness of it. So simple chi-square is defined as data minus theory by error whole square, as you can simply define if there are no correlation. And covariance matrix is also there if you need the covariance matrix. If, for example, supernova data, the covariance matrix is there with systematic uncertainties, right? So this is the grid-based search. Let me cut it off from here. Okay, so you see what I am doing now is I am defining this supernova chi-square where I am simply calculating, where I'm calling the chi-squares, okay, distance modulus for the values. So it depends on parameters, okay, it depends on this theta I set. So theta is basically the parameter set. So it comes with omega matter and h naught. Again, as I have mentioned it repeatedly, that H naught cannot be constrained, but this is just to show the fitting, how fitting is done, where I am using a toy model because the error covariance matrix that I am using to be diagonal is not correct. So you can see that it depends on two parameters, omega matter and H naught, and I am calling distance modulus for all those points. Okay, all those points, and I am calculating the supernova chi-square and log likelihood. Then I'm defining log likelihood. Remember, it is minus half chi-square. Okay, this we are going to need later. And then find best fits. This is a find best fit routine that I am using. Let's say I am using a 10 cross 10 grid. I have written, see, I have defined the best chi-square to be a very bad value, 10 power 30. So it will save the chi-square for different range for, let's say, I equal to 1 to different values of omega m and j equal to 1 to different values of H naught. So if the chi-square that it finds for different parameters, if one parameter, the chi-square is lesser than the last parameter, it will save that and it will discard the other parameter. Okay, that is how you are going towards a smaller value of smallest value of chi-square. And the grid based, you are actually exploring the whole grid, and therefore thereby you are actually going towards the best fit, but you are by selecting and rejecting. Okay, but you have to search the entire grid. So please run this one. Okay, chi-square simple is not defined. I didn't define this one. Let me just run this. So this is a chi-square test. I am for a simple value. I just tested that, and chi-square test is giving me a chi-square of 657. And if I run the grid search, this is the chi-square that I am getting, 576. My best fit value is 30% of matter, 0.3, and 68 is the value of H naught. If I make it 20 cross 20, it will take more time. (24% of matter) and 565. I can even get to 565. Chi-square is lower. So if you keep on doing that, you will be able to get the better and better fit. Yes, there is a question: what fitting procedure would be used in cases where errors? Fitting procedure is the same. What you have to do is that you need to change your likelihood in the, so there you have to understand what is the distribution, and depending on the distribution you have to write a likelihood. Okay, so here the things that we are dealing with has normally distributed likelihood. In some cases where, for example, in one direction there are some we have one directional constraint, so there people use half Gaussian. Okay, so there lots of approximation can be taken, and sometimes different other things can be taken, but you have to take care of the distribution and then implement that. So in Gaussian, in both the cases, we know for Gaussian distribution, this is the one, and for the other one, you have to define a different estimator. Just like the chi-square, you have to define that, and then you have to connect it to the likelihood.
Sir, can you please explain that best fit from grid search line again? What is the change and what is the meaning of that?
Oh, this one. Which one? Sorry.
That one which you have just changed to 20, the bounds 100 was there.
Okay. So yeah. So let's say let's say this is my mobile. It's visible, right? So this is the x-axis. X-axis I am varying omega matter, and y-axis I am varying H naught. So this is a 20 cross 20 grid. So between different, let's say I am saying omega matter can vary from 0 and 1. Okay, 0% to 100%. And H naught can vary from 10 to 100 kilometer per second per megaparsec. And I am dividing them into different grids. If I am dividing in between 10 grids, then it is basically, it will have 0.1, 0.1, 0.1 bin width. If it is 20, then it is 0.05, 0.05. So you are basically starting from one value, and then you are going to another point. If the chi-square is better, you are keeping it, means that it is lower, you are keeping it. If it is not, you are rejecting it. Second value, keeping it, rejecting it. That's how it is done. Clear? And when I did, it is a number of tries, this 10 and 20. So in each direction, what will be the binning? So it is, I have made the same in both directions. So initially I tried with 10, means 100 grid point search, which gave me 570 or 576 chi-square. Now, if I do it finer binning, I'm getting 565. Okay. Now I am using SciP optimize. Okay, the best fit finder. Okay, so these are different routines. For example, the different types of methods are there, which are not grid based. Grid based was just to show you that how it works. But now people have written different sophisticated methods where you can simply go to the best fit much quicker. So let me run that. You see, it was taking 20 seconds for the last one, but here it took less than 1 second, and the best fit chi-square is 562. Okay, for the value 0.277 and 70, h naught of 70. So if you make it 100, it will take a huge amount of time, but it will slowly converge to this value. Okay, so we are using SciP. Okay, here. Now let's so if you plot the best plot it against that plot the line against that data, you can see that this is fitting the data pretty well. Now we are just plotting the deceleration parameter. Remember this parameter, this value I showed. So for the value of omega matter and omega lambda, if you draw the history of the universe, draw the expansion history of the universe, this is how it looks like. Okay. Deceleration with q equal to 1, deceleration with q equal to 0.5, and acceleration with q equal to minus 0.5. Okay. So these are the assignments that I also shared with you in that PDF, not PDF, but sorry, Google presentation. Should not one mention the number of free parameters alongside the chi-square, because if the model parameters are increased, chi-square may decrease, but even yes, of course, that is what we are going to do with the Markov chain Monte Carlo. This is the best fit finding routine. Okay, so we are trying to see what point fits best. Of course, it is the case. Then there are lots of other things. There are, I mean, we have to use the Bayes theorem. So for Markov chain Monte Carlo, we can get the posteriors, but then there can be integration of, then there are there are integration of posteriors, which gives you marginalized posteriors. Then you get evidence for a model. Then you compare that model with another model having equal or different number of parameters, and then you compare the evidences, and you can say which model is better or worse. Okay, does this answer your question, Anubhav? Okay, in this relation, I would urge you to go back to my inflation slide, where I plotted, I had given one table from Planck analysis, Planck 2018 analysis done by Planck team. And in the Planck team, they had explored different inflationary model with different parameters. There they have calculated the chi-square, at the same time this log b parameter, the evidence. And that showed, remember, if you remember correctly, I said if it is less than -5, then those models will be discarded. Okay. Muti is taking too much time. Are you using 100 points? For example, is if this print best fit from grid search, find best fit bounds, comma 20, is it 100? See the line I am highlighting. Is it 100? If it is 100, it is going to take a huge amount of time. Yeah, so you can stop that, but I mean, or yeah, do take it to 10 cross 10 is 100 points is not going to take much time. Okay, so now let's go back to the lecture again. Okay, the Bayes theorem states the posterior probability. Yeah. Okay, actually in next Kumar analysis we mentioned both chi-square and degrees of freedom in the tables. This is why I'm asking. MCMC is also pretty well used, but conventionally both chi-square and degree of freedom is mentioned. But this is when you do MCMC, these are already integrated over the prior range. So in those cases, MCMC or Bayesian evidence is a much better quantifier or for the rejection or acceptance of a model compared to the chi-square and just degrees of freedom. So these are called chi-square and just writing degrees of freedom. These are called frequentist analysis. Okay, and then you go to the next part, which is called the Bayesian analysis. Okay, both have their pros and cons, but if you have a non-trivial prior distribution, etc., if your parameter space is huge and non-Gaussian, then definitely you have to do Bayesian evidence calculation. Okay, so I mean, whenever you are doing MCMC, it's much enhanced or advanced techniques. Okay, so posterior probability P theta given a data and a model is given as P d theta m, for theta is the set of parameters for a model m, and P theta m divided by P d m. P d theta m represents the likelihood. You remember likelihood we discussed. P theta m is the prior probability distribution. Let's say you already know from other experiments what should be the what is the distribution of omega matter, let's say, or different parameters within the set of theta. And PDM is the Bayesian evidence of the marginalized likelihood. Which contour do we need to plot? Okay. So plot the contours. Remember, I had discussed the significance. So just run it and see what is the degree for degrees of freedom 2. You get the chi-square, and that will be the best fit. And around the chi-square, you actually get the chi-square line for the chi-square minus 2.3 if you have two parameters. If you have three parameters, then you can simply draw the chi-square line for chi-square minus plus 3.5. So it is worse, right? Chi-square plus 3.5 you have to go. Okay, that is going to give you the 1 sigma. Okay, and it is the 90%, which is not 2 sigma, but still you can say that this is 90% contour. Okay. 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 Bhaswat is saying module not found error. Okay, no. This we are going towards that. MC will come later. You have to install MC. You have to install MC. Pip installed MC. Yes, you have to install it from the terminal. Also, you can simply install it inside that Jupyter notebook. Just before going to MC, you just say pip install MC. It will install, I guess. Okay, somebody else having some problem. Toshif Alam, what problem you are having? Mini Konda return co.
Yes, sir. When I try to, try to plot distance modulus in this TIHISI on IPython node file, then that.
I am not able to see the error actually. It is not showing what the error is. Return luminosity distance. Then you may not have computed all of the cells. Have anybody else encountered this error?
I have computed a cell from the start.
You are doing it in that Psi server, right?
Yes, sir.
Then you should not face this error, because I am not able to see any
Sir,
error. I'm not able to see.
Yes,
I mean,
sir.
the error message, but it is not saying that which one is missing. So, can others help? Have anybody seen this type of error? I haven't seen this type of error actually.
Sir, actually, sir, we have to start from this TIH 3D1, and I have run the cells from import NiPy, starting from import NiPy, and then computed the cells on by one, and then reach this point, and then when I run this, then this is what's showing here, attribute error.
Okay. Okay. I would urge you to download this in your machine and then try, because if it is Psi server, then everybody is having the same answer. I think it is some problem of running it. If you are not running all the cells properly, you have missed some cells or something like that.
Sir, which cells can be missed here?
I mean, maybe the co-moving distance. Just start from the beginning, right? I mean, okay.
Yes, sir. Yes, sir. Beginning of this notebook file, na?
Yeah. You can start from even from the TIH part. You can, that is also a that is a markdown file. So you just double click that and then keep hitting shift enter, shift enter, shift enter. Means
I have done this twice, but it's
so actually the thing is that I'm not able to understand the error. It is not showing the error. Otherwise I could have helped you. I mean, I could have been able to help you because I could understand the part, but it is, I'm not able to understand what is the problem here.
me too, sir.
Yeah. So you can download it in your machine, or I think some compilation. Yeah, see.
Should I do it in Google Colab? Should I try?
Yeah. Of course, it will work in Google Colab. Why shouldn't it?
Sir, any other folder? You said that all other folders should be here. I mean, in this notebook file.
Yeah.
And I even unzip the data file.
Yeah.
So then I try to run it. The theory, should I run it or do something previous? I mean, any preliminary task before running this.
No. See, TIH workshop. See, I'm simply starting from here. Okay. If you do not have a library, it will show you like MC is not there or something. See, you can actually run all the cells. So or you can do it from here also. This is the run the selected cell and advance. Click, so that you don't miss any cells. Okay.
Achha.
Okay. Please do that.
Okay, sir.
Then sir, 1 minute. My theory dot constant, that is not working.
No.
Hello.
Theory constants. It is not
theory constants as constant. That is not working.
No, it is theory constants dot py.
Theory constant dot.
Theory constants dot py. That is the name. See here. I'm circling it. You are able to see my mouse, right?
Yeah.
Theory constants dot py. That is there. I have clicked on that. Actually, I am in size server as well. Theory constants dot py. And here you just say, instead of constants, you say import theory constants as constant. See, that is why it is very important to let me know as soon as you hit this issue, because now we have made lots of progress and we went to the middle of that notebook. And now if you are stuck at the third cell, that means that there is something missing fundamentally, right? So okay, the thing is that it has changed.
This is also happening to me. File changed. This pop-up message is coming.
Are you running it in my file or okay, there is another theory DE1. There is somebody who has okay again please. Okay, see, this is the copy of that. Okay, so there is a copy that has been created. You have the right permission, but please do not copy it. Okay, copy it in my directory, copy it in your directory. Okay, so you see, I'm advancing to the, see, it is working. I mean, I don't have any extra things. I mean, you can simply just install all these things and then work with that. See. All right. Okay, so let me just proceed. So Markov chain Monte Carlo, there is this article you can read. Okay, so I'm going very quickly here. So you start with an initial guess. Okay, let's say I'm trying to search the parameter space of omega matter and h naught. I'm starting with an initial guess. Let's say omega matter is 0.1 and h naught of 90 or something like that. And I am giving it an initial width where it will generate random numbers to begin with. I have, let's say, n number of workers, 100 numbers of workers, let's say. Each one is going to generate random numbers between around this point, omega matter, around the starting point, and it will you will have to also give an initial width so that it can generate the random number within that width. Okay, and that is where you are going to get initial samples, and then you produce chains of new samples. How you are going to do that? You take another random number, and each sample is created from the most recent sample with a proposal. Depending on the proposal, the sample can either be accepted or rejected. So in higher dimension, as you can see, even in the 2 dimension, grid likelihood is time consuming, and for very high dimension, it is not feasible. That is why this experiment or this trial was needed. I wanted to show you that the grid likelihood, grid-based search is not very good or not very efficient. You are able to see that if it is 100 × 100, it's taking forever. Markov chain Monte Carlo performs a random walk to sample the multidimensional parameter space. Cosmo MC, for example, uses this Markov chain, this Monte Carlo, and Markov chains. The chains are Markovian, and it uses Metropolis-Helsing algorithm, which accepts better likelihood points and accepts lower likelihood points with a probability defined by the ratio of the likelihoods. Otherwise, reject if the ratio is too low. And these are the different walkers. So there I am plotting, like, let's say 50 lines randomly, 50 walkers, let's say. Okay, so 50 walkers are walking, and it is going to that direction. It goes to another. So let's say I'm taking 1 point. Okay, I'm taking 1 point. Yeah, MC cell is going to take too much time because it is going to take it is going to take 30 minutes or something like that. 500 iteration. You can reduce the number of iteration and then run again, stop that, and then you can run again 50 iteration. But it is not going to be very effective in order to get the parameters. You can do it at your home, okay, or I mean after the lecture. So you can see that this is the iterations are going on here. You can also reduce the number of workers. Apart from 100, you can make it 20 or something like that. And you see, it is. It takes 1 point here, it accepts the point, it takes another point here, but it is rejected. Then it comes back. You see, it takes a point in the other direction. Then you see then the number of points are accumulated. From those accumulation, you can see what are the distribution of points in that region. Okay, just see. Here the distribution is most dense. From here you can understand what is the 34%, that means 68% line, 95%, and 3 sigma. Okay, this is just a schematic diagram. Post processing is initial guess can be away from the confidence ball. So you have started, let's say, initial guess of 0 matter. So Markov chain Monte Carlo will take time to go to a reasonable parameter space. So therefore, you remove some of the initial points. Usually 10 to 30% initial samples are rejected. This initial phase is known as the burn-in phase. And then the marginalized posterior is basically the likelihood times the, for example, if you want to get a parameter, there are 2 parameters, x and y, you get this 2-dimensional likelihood, and then you integrate over the prior range of y times dy. You integrate this in this y direction, you get the posterior on the x. Okay, that is how we get the posterior probability distribution. This is from MC and this is from Cosmo MC. Again, I have said it again and again, you must use a covariance matrix here. This is a toy model example. From there, in the Cosmo MC, you can understand what is the omega matter, 0.287. This is the best fit we also obtained from the SciP search, right? Lower one is this, means that, so standard deviation is this, so lower one is this, and the higher 1 sigma is this one. Lower 2 sigma, higher 2 sigma. And omega lambda is just 1 minus omega matter. So these are the marginalized 1 sigma, 2 sigma, and 3 sigma limits. Samples of QFZ you can find there. And okay, another thing is that Cosmo MC I'm going to discuss. Again, the points that you search, if you simply plot the chi-square by 2 minus log likelihood, matter density in matter density, you will look this will look like this. So you see most points are concentrated here. Here there are very little points, and the color bar that is showing here are basically the values of H0. You can also zoom in here. Then what I'm plotting here is marginalized likelihood. What I'm doing is that I'm just exponentiating that and dividing by the e power minus chi-square best fit by 2. This is the marginalized likelihood that you can get. And you see that for different, so this is not a one line, right? This is showing an area. So for example, if I take this value of omega matter, chi-square or likelihood can be this value, or can be all these values combined, not combined, all of the other values, because H0 is varying. H0 is going up and down. So then what you do is that you integrate this over H0, over the H0 prior, and you get this line. This confidence contour, this probability distribution. Okay. And if you want to see that bivariate normal distribution here, the posterior, this is in the H0 and omega matter plane. Okay. These are the concentration of points, as you can see. So this is the higher value of likelihood. These are the lower value of likelihoods. Okay. This is the constraints from dark energy using different observation, supernova, BAO, CMB, etc. As you can see, in this case, supernova alone cannot constrain dark energy pretty well. If you have BAO, they cross each other, and if you have CMB, they also cross each other, and finally you get to you obtain this middle gray line, which is very much constraining, and it is saying that your omega k has to be very close to 0. This line is actually omega k equal to 0 line. That means omega matter plus omega lambda equal to 1. As you can see, this is the omega matter plus omega lambda equal to 1 line, the black line, and this is just saying that it is very, very well consistent with this theory, with this theory that our universe is flat. For a non-flat universe, get constraints. This is your assignments. Now let me go back to that. So again, I am not showing any dark energy parameterization here today. Tomorrow we are going to do that. This is just the dark energy density which we are constraining. Okay. Now we do the MCMC. You will get this type of contours. You get the bounds on parameters using this. These are percentiles. Okay. So 50 percentile is basically the mean. 84 is 50 plus 34. 16 is 50 minus 34. So you see, you put it in that plot. You get from the posterior distribution, you make it cumulative. From the cumulative distribution, you see where the 50% lies, 0.5 and then 0.84 and 0.16. So those values you just ask the code to calculate. So this is showing that omega matter is 0.2784 and plus minus this. Okay. 0.019, and here you see my Cosmo MC results are showing You see 0.019. They are very good, consistent with each other. Whatever I am getting from MC and Cosmo MC, now I'm showing you the Cosmo MC and why we should use Cosmo MC instead of MC in this type of cases, and why we use actually we just not
Sir,
use.
So sorry to interrupt. In the MCMC case, where are we setting the initial value for omega m and the width?
Yeah, here. Okay, I can show you here as well. Yeah, OM best fit, H not best fit, and width is
Okay, so
0.1
it is 0.1 is the initial case and the width is 10, like that.
no, omega best fit is the
Omega best fit is 0.1.
no, omega best fit is okay. So this is these two values are the two values of the parameters initial guess, and 0.1 is for the omega matters width and sigma, initial sigma within which it should take the values, and 10 is the width of H naught. So the first line is showing the initial value, second line is showing the initial width of the parameters. Okay.
Okay.
Okay. Here what I am doing is that I am defining a proper chi-square that is defined with difference. Data minus theory is the difference. You remember, I am taking the transpose and using the inverse covariance matrix. As I said, I'm using it from Cosmo MC's inversion, so it is already inverted. So this is SN Cov W mat. So this is the inverted covariance matrix, including the systematic errors. Okay. So if you do that, you get the correlation, and when you calculate that, when you calculate the likelihood and give that instead of that simple chi-square likelihood, chi-square from the likelihood from the simple chi-square for the supernova, you can see I do not get any constraint on H naught. H naught is nearly, the posterior of H naught is nearly uniformly distributed. When you do that, you see H naught is not constrained. 65.11 plus minus 23. And this is something was the what I had provided as the minimum and maximum value, that it should not go beyond these values. So here we can only constrain omega matter, therefore omega lambda, because it is 1 minus omega matter, and we are not able to constrain H naught. Clear? Good. Now I would like to show you the Cosmo MC and why we are using Cosmo MC. I have given you download the version of Cosmo MC that I provided. Actually, this is the March 2014 version of Cosmo MC, because all the later version of Cosmo MC doesn't use background parameterization. And if you use background parameterization, it is going to show you certain errors. Okay. And therefore, compilation errors. So that what I provided here in this Jupyter lab, in this folder, in this file, actually, I'm sorry. Yeah. Cosmo MC March 2014. You can simply copy it. Please do not copy in my folder. Okay. File.tar.gz is copied, I can see. So please just copy this file or copy this folder, Cosmo MC March 2014. Chi-square contour is also not closed, is it? It is elongated along one particular axis. Is it also inactive? In which case, H naught or omega matter? H naught. Yeah, it is not closed in any direction here. That is because we are using the systematic covariance matrix. That is why it is not. This is not at all dependent on H naught. Okay, so my data is not dependent on the variation of H naught. Okay, that is marginalized out in the covariance matrix. Okay. File.tar.dz, you don't have to copy that. Somebody has copied a file.tar.dz there, but you don't have to copy that. You have to copy this one, Cosmo MC March 2014.zip. Please, I'm telling you repeatedly, don't copy in my folder, because it is going to be, I mean, I have all the copies in my machine. It is not a problem for you. You just download this Cosmo MC March 2014.zip, Ankit. Just download that here. You can download it, download and from the Sai server and run it. Now I have to show you the Cosmo MC run. Are you able to see my terminal?
Yes.
Okay. So .ini. So Cosmo MC runs with different likelihoods. Okay, so there are lots of likelihoods. For example, the likelihood that I defined is written here. Is can be found if you add this union.ini. Union is the data name. You just comment out all the other likelihood. For example, batch, low like, CAMSPEC, etc. All the BAO, HST, and everything. And the last, these lines are important. For example, I am doing the dark energy analysis with supernova. Use CMB. I don't want to use CMB. False. Parameterization background. In that parameterization, I need just 2 parameters. Omega matter. You can also open others, but 2 parameter omega matter varying from here to here. H naught from varying from 70 for 70. So this is the mean value. Okay, and that you are saying that this is the initial value. These are the minimum value and maximum value 0.1 to 0.9, and these are the widths. Okay, one is proposed width and one is what you one is jump width or something like that. If you have it, you just have to set one of them to a small. I think this is the batch one params before. Okay, it doesn't exactly say, but you have to put the first one to be initial width to be 0.1, and the proposed width also you can say 0.01, or here also both of them 0.01. Here it is 1 and 1. Neutrino number of massive neutrinos is 1. In the lambda CDM baseline model, we are assuming it to be 1. Total mass of the neutrinos is 0.06 electron volt. This is assuming the normal hierarchy, and this is the minimum value in the normal hierarchy. That is what we are setting it to be. It is flat, omega k equal to 0, W equal to -1. So it is lambda CDM, WA equal to 0. Neutrino species is 3.046. Okay, action equal to 0 means we are doing Markov chain Monte Carlo. Okay, so I have already make clean and make all. So this Cosmo MC executable will be created. What you do is that you say MPI run minus NP2. Let's say I'm just using two cores in my machine. Cosmo MC test.ini. In test.ini, I said this is going to be my name, DE_SN, and this union.ini has the data. Okay, if you go to that file, batch1 union.ini, you will be able to see that which file it is directing to. Those file I have also used in my notebook. Okay, let me just run that. I hope you are able to appreciate now why we are using Cosmo MC. Okay, so the whole Markov chain Monte Carlo process is completed within, let's say, how much? 5 seconds or something like that. And it is converged. So we have a convergence criteria. I'm not going to discuss that. As you, study, you will be able to understand that. There is some question. Provide the changes you have made later couldn't follow all of them. If you download that, the changes are already there. You don't have to do that. And I have already made the changes. And it is also provided all the changes that are there in the test.ini. The changes that are there are written in the red lines in this particular file. Particular slide. All right. Okay, great. So if you have the access to the slides, you will be able to do that. Now, where are all the results? In the chains. These are called parameter chains. Okay? It's freezing. Strange. So you see, I have run into two CPUs. So 1 and 2 files are created. So as you can see, if I just open the context of, open the contents of one, the first one is the weight with which they are accepted and the points are accepted. Second is the likelihood, minus log likelihood. That means chi-square by 2. Third is the value of omega matter. Fourth is the value of H naught, and fifth is the omega value of omega lambda. But omega lambda is not a free parameter. Remember, this is just a derived parameter. Okay, so we are just for the sake of plotting, we are deriving that. Now let's go to the Jupyter lab. Here, I have created a not here. My mistake. Here. You use getDist for post processing. So as you can see, getDist post process is here. I am importing the plots from getDist. I am asking them to compute 30% of initial stage. As I said, 10 to 30% of the points has to be rejected. So I am saying ignore rows 0.3. Means 0.3 fraction has to be ignored, and plot the triangles omega matter, H naught and omega lambda. Do not know why it is not plotting here. I'm going to show you after exporting. Export DESN.pdf. Then I'm doing the analysis and asking what is the 95% limit. You see, omega matter is 0.28 plus minus 0.1, plus of 0.1 minus 0.09. H naught cannot be constrained. So therefore, omega lambda is 0.72, 72% of dark energy. Okay. And if you want to see here, omega matter, Cosmo MC here, you can simply, or here actually, you click on this DESN. This is the constraint that you can get from the Cosmo MC. Okay. Omega matter is this. Omega H naught you cannot constrain, and omega lambda is this. Okay. All right. Then let's go back to this slide. Oh, sorry. Okay, your assignment is to constrain omega k and omega matter. Okay, there what you have to do is that you have to definitely change these values, these expressions. For example, here you have to set them as, okay, so this is, I think, wrong. Yeah, it's correct. CDT by AT integration. So F is sine or sine hyperbolic, as I have discussed. It should be in your first lecture's slides, so you can have a look. And this is going to be one of the assignments. If you are able to get this and match this plot, then you will learn a lot. There is one very simple way. I would urge you not to take that. Let me also show that way. Yeah, this is what I showed, right? I mean, you can simply say what is omega k here. All the codes are there. Just like here, you can also give the search window of omega k, and you will be able to get the answer. But I would strongly urge you not to do that, because here you don't have to make any changes in the code. If you do it in the notebook, you will learn a lot, because you will understand what is the how distances change if you change the spatial curvature of the universe, and how these are constrained using the data. And you will be able to understand using the grid based also. So these are different steps. You start with a grid based search. You define chi-square for simply you define a simple chi-square, simple likelihood. Do a grid based search. You see that it is failing after some time. Then you take a much better search. For example, site you optimize a different method. Then you go to a better definition of chi-square, the complete definition of chi-square, the proper one, using the full covariance matrix, write the likelihood, then you do a MCMC. That's how you learn. So it is better that you learn it properly. And that's how, I mean, I would urge you to follow the notebook instead of just running through the Cosmo MC, not as a black box, okay? Cosmo MC tomorrow I will discuss. What I would urge you to do is that please run it. Please run it either in your machine. If your machine doesn't have MPI F90, just see how you can get hold of an MCMC. So apart from just me discussing the Cosmo MC, it is better that you have some questions and I can answer them. So just ask your friends how you can get hold of a Unix machine in your department or in your cluster. Okay. As you can see, this takes like 3 seconds to run. Please repeat the part of running test.ini. I showed you how to run. I'm just showing you how to run, but you should run it, and please ask me the question tomorrow. Just this. Okay, I'm removing RM chains, removing chain files. So MPI run. So it is MPI is a parallel architecture. It is saying that take 2 nodes. Okay, sorry, not 2 nodes, 2 cores, 2 CPUs, and run Cosmo MC with the parameter values that are written, parameter values, likelihood values, everything with the settings that are written in the test.ini. As soon as you run that, you see that Monte Carlo changes. Monte Carlo starts, and it basically starts collecting samples, and at some point of time, these are the convergence. Okay, at some point of time it will converge. It will say that if the convergence is lower than 0.03, it is going to finish the program. So it is going to 0.015. It is able to see that, and then it's stopping the program. Okay, so MPI run with pip. No, this is not a Python, right? So this is, I mean, it is independent of Python. So probably the MPI architecture of Python can be installed by pip. I do not know, but if you are having a Ubuntu machine or any Unix machine, somebody has shown how to install that. Sudo apt-get install OpenMPI developers, things like that. You can just Google it. For if you have Mac, then also you just search it. It can be downloaded from homebrew installation. Okay. Any other questions?
Sir, I had a question.
Yep.
So, what does the off-diagonal components of the covariance matrix of the supernova dataset represent?
They are the correlation between different data sets. Okay. So
they are independent supernovas, no? So how are they correlated?
When you do this, when you they are independent supernova, but when you are doing this analysis, when you are doing their analysis in the same analysis umbrella, they become correlated because okay, and that's a good question. Okay, how to answer that in terms of the analysis? Even in terms of other data sets, it happened. Okay, in the supernova, what you get is the light curve. Okay, and what you do is that all the supernova, for example, you take you take the set of supernova, let's say from first observation, first set, second set, third set, for let's say you have 10 sets, and they have different absolute magnitude, okay, from their and the analysis system is different in different cases. Salt is the one that is used to get from the light curve to the distance modulus analysis, to distance modulus calculation. And in those cases, when you when you get the data, okay, so to be very honest, I would say that since I have not done this salt analysis, there I am using also it as a black box. So therefore, I will not be able to answer your question completely. Okay. So this is called the covariance matrix including systematic. So when you combine all these data sets, so my partial answer is that when you combine this analysis, all the analysis of the supernova, since you are doing the same trying to keep them in the same footage, then your errors become correlated. Error becomes correlated, although these supernova are independent. All the observation of the supernova are independent. Another thing is that if you are using even the same supernova, same set of supernova using one particular observation, then also they can be correlated because you are using the same system, right? So therefore, the errors can remain correlated as well. But this is an answer with which I am also not satisfied. So let me dig up a little bit and get back to you. Okay. If I'm not able to answer it tomorrow, just write back to me in email, and I will try to find it out with the people who are experts in the supernova light curve analysis, and then I can try to answer that. Okay. This is a very good question, by the way.
Okay, sir. Thank you.
Yeah. Thank you very much for the question. Yeah. Any other questions?
Sir, can you please repeat how to constrain omega k versus omega m?
Just the same way I showed you. Omega matter constraint, you have to have another parameter. You have to include that. At the same, this part is for the analysis, but the distance measurement, you have to include the curvature there as well, right? Sine and sine hyperbolic, etc. And those formula I had already given to you, in my first lecture.
Okay, sir.
Any other questions? No? Okay, let me stop share. Tomorrow we are meeting at the first hub, 11:30. And I will, two students said that I should explain the Cosmo MC mode, the test.ini mode. So please explore and get back to me tomorrow with your specific questions. And then after discussing that, I'm going to go ahead with the dark energy with specific examples of dark energy, parameterization of dark energy, either equation of state parameterization or parameterization of dark energy density, or having a theoretical model of dark energy, for example, having a quintessence model. Okay. All right. Then let me stop here.
Okay, so thank you very much, Dhiraj, for one more wonderful session. And that's all for today. Tomorrow, as he said, tomorrow we'll meet at 11:30 once again. And that will be the last session of this workshop. Okay, see you all tomorrow.
So, bye.